In this video, we're going to discuss time dependence in quantum mechanics. So far in this course, we've ignored time dependence for the most part. And now we want to see how it plays a role. Now we're still only going to consider the relatively simple case, which is what's true for most of chemistry, where time does not explicitly appear in the Hamiltonian. So we're solving the time-dependent Schrödinger equation, but H does not contain time as a variable. If that's true, then we can use separation of variables to decouple the time-dependent Schrödinger equation into two separate differential equations. One, the standard time-independent Schrödinger equation we've been using for the most part, and then there's a separate differential equation describing the time dependence. Now this differential equation can actually be solved pretty easily, and the solution to this is that 5t is equal to e to the minus I times the energy of the end state times time over h bar. And so then to construct our overall time-dependent wave function, we just take the energy eigenstates we get from solving the time-independent Schrödinger's equation, the psi n's, and then we multiply each psi n by the corresponding phi n to get the time dependence. So our overall wave function as a function of position and time will look something like psi n of x times e to the minus I e n of times t over h bar. So we're essentially just multiplying this time-independent solution by some sort of oscillatory phase factor. Now it's hard to have a great intuition for what e to the I something does, but you can use the expansion that e to the I theta is equal to cosine theta plus I sine theta to get some sense that this is adding some oscillating piece to it, even if it's a complex oscillation that therefore makes it a little harder to visualize. So let's just do a basic example. In the simplest case, we could have something like the particle in a box, and we could write down the wave function for the n equals 1 state. So psi 1 of x is equal to square root of 2 over L sine pi x over L. Now the energy for this state is h bar squared pi squared over 2ml squared. Or you could also expand out the h bar to get h squared over 8ml squared. But I'm going to leave the h bars here because it's going to be a little easier when we start throwing in the time-dependent part. So this is our ground state for the particle in a box and its corresponding energy. If I want to write down the time-dependent wave function for this, because time is not a variable in our Schrödinger equation, we were able to do this separation of variables, and therefore we can go ahead and write our overall wave function as psi 1 of x times the time-dependent phase factor, this e to the I e1 t over h bar. And E1 is just this energy we have up here, so if we want we can plug that in where we have E1 here, cancel out a few terms, cancel out a factor of h bar, and we get this final expression. So this is our time-dependent wave function for a particle in the n equals 1 state of the particle in a box. So it's quite straightforward. If you're in an energy eigenstate, all you need to do is multiply it by e to the minus I e t over h bar, where the E is the energy of that particular eigenstate. And that's the one key part. You want to be sure to be using energy for the particular eigenstate that term is modifying. Here's one more example. Go ahead and try this one, pause the video, and then I'll hit play when you're ready to see the answer. Try writing down the time-dependent wave function for the particle in the box in the n equals 3 state. Alright. The solution to this is going to be basically the same. We're going to take our psi 3 of x, multiply it by the time-dependent phase factor, this e to the minus I e3t over h bar, and I can plug in this energy E3 in here, and I canceled out a factor of h bar, and I get my final result. Alright, but the more interesting behavior happens if we are not in an energy eigenstate. This gets a little more complicated, but it's still not a big deal. Whatever that energy, whatever that wave function we have, it may not be a single energy eigenstate, but it can always be expressed as a superposition or linear combination of those energy eigenstates. So for example, of two particle in a box states or something like that. So whatever my phi of x, whatever my current state is, I can express it in terms of the energy eigenstates. In this example I've made up by saying it's expressed as 1 over square root of 2 times the n equals 1 particle in a box state plus 1 over square root of 2 times the n equals 3 particle in a box state. If I want to write down the time-dependent version of this wave function phi, I just need to multiply each of the energy eigenstate pieces by its own time-dependent phase factor. And so notice psi 1 gets multiplied by an e to the minus I e1t over h bar, and psi 3 gets multiplied by an e to the minus I e3t over h bar. So the energy up here in the exponent is different depending on which energy eigenstate it's modifying. But so we just express our arbitrary wave function in terms of the energy eigenstates, and then multiply each one of those energy eigenstates by the appropriate time-dependent phase factor. And again, here, if we wanted to be more complete, we can specify that psi 1 in this case is this wave function for the particle in the box for the n equals 1 state, psi 3 is the n equals 3 state, which is this wave function, and then here are the corresponding energy values that would go up in the exponents. And so we can do this quite readily for any arbitrary wave function just by expanding that wave function in terms of the energy eigenstates and then scaling each one of those by the time-dependent phase factor. Let's do one more example. Again, pause the video, try and work this example, try writing down the time-dependent wave function for this phi of x, and hit play when you're ready for the solution. Here we go, here's the solution. We see that, again, we just take each one of these terms. The expansion is writing phi of x in terms of energy eigenstates psi 2, psi 4, and psi 5, and each one of those just gets multiplied by the appropriate e to the I et over h bar, where I've substituted in the correct energy corresponding to the eigenstate that's being modified. Psi 2, psi 4, or psi 5 gets e2, e4, or e5 respectively. Alright, once you have the time-dependent wave functions, then you can compute all the usual quantities as a function of time. And so, for example, if we want to look at a probability distribution or maybe check that the wave function is normalized at some time t, we're just going to take psi star psi or phi star phi, depending on whatever our wave function is, integrate over all space, and evaluate it at some particular time t. And so then we can get a result where the probability distribution or the normalization varies in time. Similarly, if we want an expectation value as a function of time, we calculate expectation values with the same sorts of expressions, with the wave function's complex conjugate on the left, the operator corresponding to the observable we're trying to measure, and then the wave function again. And we integrate over all space, and that'll give us a result that will, in principle, depend on time. Now, the one caveat here is, so far in this class, we've typically used real wave functions. But with these time-dependent pieces, the e to the minus I e t over h bar is complex. So it's an important time to start paying attention to your complex conjugates. You need to make sure that you properly change the sign of each instance of I when you take the complex conjugate. So let's do some examples. One interesting thing is it turns out that when you're in an energy eigenstate, the time dependence typically cancels out, and that gives us what's a so-called stationary state. And so to see this, we can take the example of a wave function, capital psi, that is the n equals 1, say, particle in a box state, times e to the I e1t over h bar. So this is our time-dependent wave function for something in the n equals 1 state of the particle in the box, for example. How does this probability distribution vary in time? Well, I can look at psi star psi and go ahead and evaluate that. So I have psi 1 star times e to the plus I e1t over h bar times psi 1 e to the minus e1t over h bar. So notice I have the plus in the exponent here because I've taken the complex conjugate of this wave function, which changes the sign of I. So I go from minus I to plus I. Now if we're talking about the particle in a box, psi 1 is actually real valued, so there's nothing actually changing between psi 1 star and psi 1, but I still marked it as the complex conjugate just for the sake of clarity. Now we go ahead and multiply this out, and we get psi 1 star psi 1 times e to the plus I e1t over h bar minus I e1t over h bar. And so here I use the property that the e to the a times e to the b is equal to e to the a plus b. So I was able to combine the exponents of these two expressions and get this. But you'll notice the two things in the exponent here cancel each other out. So actually, this is equal to psi 1 star psi 1 times e to the 0. And anything to the 0th power is just 1. So in other words, this is just equal to psi 1 star psi 1. So there's no actual time dependence in this case. The time dependence completely cancels out when we're in an energy eigenstate. And that's why we call these stationary states. On their own, they have no interesting time-dependent behavior. And this is why so often in chemistry we can ignore time dependence, because we'll often be talking about things like spectroscopy where we're considering transitions from one stationary state to another, and any sort of meaningful time dependence largely cancels. And so things are pretty simple if we are in an energy eigenstate. We don't really have to worry too much about the time dependence. But what if we're in a superposition of energy eigenstates? So we're in some other arbitrary state that's not just one energy eigenstate. Then we represent it as an expansion of energy eigenstates, multiply each term by the time-dependent phase factor like we saw earlier, and we might get some wave function that looks like this. For example, phi of x and t is 1 over square root of 2 times psi 1 times e to the minus I e1t over h bar plus 1 over square root of 2 psi 2 e to the minus I e2t over h bar. Again, and I'm using it as an example of particle in the box system. So let's look at how the probability distribution for where we're going to find the particle varies in time for this wave function. So we start off taking psi star psi. So I have here psi star, phi star phi. I have here phi star and phi. Plug in the expressions. Again, I'm taking the complex conjugate here. So my e's to the I changes sign, so it goes from negative I to plus I in both cases. In this case, I was using the fact that we're talking about the particle in the box where the wave functions psi 1 and psi 2 are not complex, so their complex conjugates are the same. That's just going to allow us to do some slight simplifications later, make things a little easier to understand. So here I've taken phi star phi. Again, just being aware to make sure I took care of the complex conjugation in the exponents. I can go ahead and multiply all this out, and when I do it, I'm skipping a little bit of algebra, but it looks basically the same. We're going to do the FOIL method where we take the firsts, the outers, the inners, the lasts. Here's what I get from multiplying the firsts. Oh, I guess I actually apologize. I inserted the stars again here, but we get psi 1 star psi 1 e to the 0, psi 1 star psi 2 times this energy difference plus psi 2 star psi 1 times this energy difference plus psi 2 star psi 2 e to the 0. So that I got by doing the FOIL method. Again, e to the 0 is just 1. So I can go ahead and simplify, and I've collected up the terms. The first term is right here, psi 1 squared. This fourth term gives us psi 2 modulo squared. And then, using the fact that these are psi 1 and psi 2 are real, I can factor out the psi 1 and psi 2 from the second and third terms and just group the exponential pieces. And you get this sort of expression. Then you can use a trig identity that says e to the minus I theta plus e to the I theta is equal to 2 cosine theta. So this expression here is actually equal to 2 cosine times the e2 minus e1 times t over h bar. And so we get an expression that looks something like this, where I've now defined this new value omega, which are these constants e2 minus e1 over h bar, just to make it a little easier to look at. And so essentially what we see is if our wave function starts as a superposition of multiple energy eigenstates, we end up getting a time-dependent probability distribution that looks like the probability distribution for state 1 plus the probability distribution for state 2 plus some time-dependent oscillating factor that somehow will change these two. In this case, it looks like psi 1 times psi 2 times a cosine omega t. And the frequency of these oscillations has to do with the energy difference between the two states, E2 minus E1, then divided by h bar. And then we can start asking things like, well, is this probability distribution normalized for all times? And so, in other words, is the integral over this phi star phi equal to 1 for all times t? Sorry, that should be a star right there. And so we could go ahead and take this integral, and basically we worked out on the previous slide what phi star phi was, and so it's equal to 1/2 psi 1 mod squared plus psi 2 mod squared plus 2 psi 1 psi 2 cosine omega t. Break this up into three different integrals: 1/2 times the integral over psi 1 squared, 1/2 times the integral over psi 2 squared, plus cosine omega t times the integral from 0 to L of psi 1 psi 2. So I pulled out the cosine omega t from the integral because it doesn't depend on x, so it's a constant as far as that integration is concerned. This first integral is just the normal integral we do for normalization within the particle in a box. So we know that this first integral is just going to equal 1. The second integral is also going to equal 1 because it's the standard normalization for n equals 2 state in the particle in the box. And this third integral, if you work it out, it turns out this third integral is equal to 0. That's not obvious just by looking at it, but if you go ahead and were to solve the integral, plugging in the n equals 1 and n equals 2 states for the particle in the box, you would find that this integral is equal to 0. And so in the end, we get 1/2 times 1 plus 1/2 times 1 plus cosine omega t times 0. Or in other words, this whole thing sums to 1. So yes, our wave function is normalized for any time t, which is good. It would not make sense if we had the normalization of our wave function changing as a function of time. That would say at one point we had a 100% chance of finding the particle, and maybe sometime t later we now only had a 70% chance of finding the particle somewhere, and later it was a 150% chance of finding the particle. That wouldn't be physical. So to have the physical meaning of a probability of finding the particle somewhere in space, it should always remain 100% if we're considering all possible spots the particle could be. Alright, finally, how does the average position for this particle in a box wave function vary with time? This time it's going to be very similar, but this time to try to make things a little different, a little more transparent in some ways, and also work with the Brockett notation, I'm going to do it using the Brockett notation. So I'm writing our wave function phi of x and t as 1 over square root of 2 of state psi 1 in the ket, e times e to the minus I e1 t over h bar plus 1 over square root of 2 state psi 2 times e to the minus e2 t over h bar. So it's the same state we had before. The only difference is I sort of turned these to kets. Now we're going to calculate the expectation value by taking phi x phi. Everything's going to look basically the same as what we did on the last few slides, except now I have the variable x here in between the two wave functions coming from my operator x. Multiply all this out, and I'm going to get, and again, having some of the terms where I get e to the 0 going to 1, so I don't worry about those. I end up getting 1/2 times an expectation value of x for psi 1 plus 1/2 an expectation value of x with psi 2 plus a cosine omega t times the expectation value of psi 1 x with psi 2. Now we already know from the particle in a box that the expectation value in any single eigenstate is L over 2. So this first integral is just equal to L over 2, the center of the box. The second integral is equal to L over 2. And then this third integral, we get cosine omega t times the integral from 0 to L of the n equals 1 wave function times x times the n equals 2 wave function. Go ahead and carry out that integral. I'm going to skip the work, but you could carry it out using the sorts of techniques we've already talked about and using the integrals in the table of integrals, and you end up getting this expression. We get a factor of L over 2 from the first two terms minus, from solving this, 16L over 9 pi squared cosine omega t. And so in other words, we end up observing some time dependence in the average position of the particle. So we have some probability distribution. We saw earlier that the probability distribution sloshes around the box with some dependence according to cosine omega t, and accordingly the average position of providing the particle also sloshes around the box as a function of t. To look at the time dependence a little more clearly, I've plotted the system we've been talking about, where the wave function is the superposition of the psi equals psi1 and psi2 particle in a box states, and the red curve is plotting the probability distribution and showing how it sloshes back and forth. The little arrow in the expectation value of x is showing the average position as computed according to the formula from the last slide. So you can see that we get some time dependence of the probability distribution for finding the particle once we have that mixture of energy eigenstates. In contrast, if we were in just the psi1 state or just the psi2 state, then we wouldn't see any meaningful time dependence in the wave function in terms of the probability distribution or the expectation value or any other properties.